There's a countdown now. Hasn't started, but there's a timer.
Just a second.
Yep. Well, live.
Shrikant, you can start.
Hello. So, hello everyone. Welcome to Set Celestia's first lecture of the year. Um, today we have with us Professor Cole Miller from the University of Maryland, the US. His work in the fields of gravitational radiation and the implications that this has on the future of modern science was very interesting for us, and he was gracious enough to accept our invitation. We're very pleased to have you with us today, Cole. Thank you. Yeah, I hope you all enjoy and learn something from here. We'll be taking questions at the end of the lecture. So if you have any, leave them in the chat.
All right, thank you very much, Shrikant. I am honored by the invitation. I'm sorry I can't be there in person, but at least we're able to communicate across the airwaves. I'm going to tell you about gravitational waves or gravitational radiation, which is something that has emerged with a vengeance over the last just few years. I'm going to tell you about what it is, what can produce gravitational radiation, what we've learned, and the future. And I hope that by the end, you will be able to share with me the joy of gravitational radiation. I'll start by just mentioning a few basics, and then I'm going to show you a quick video, and then we're going to get into how it is that gravitational waves can be produced and how they cannot be produced. Gravitational waves are a fundamental prediction of Einstein's theory of gravity, which is general relativity, or GR. There is no Newtonian equivalent. The usual thing, which many of you may have seen, is to think of the effect of gravity as warping space-time. A common picture to have in your mind is a rubber sheet. If you have a rubber sheet stretched flat and you roll a light thing like a ping pong ball across it, it's just going to go in a straight line. But if you put a heavy thing like a bowling ball on that sheet, then it warps the rubber sheet, i.e. warping space-time. And if you have, again, your light thing like a ping pong ball, it will follow the curve of the sheet. And this is gravity. In addition, if we want to push the rubber sheet analogy a bit further, we can imagine two bowling balls moving around. And if you did this, you would create ripples in your rubber sheet. And in the same way, there are ripples produced in space-time. These ripples, according to general relativity, propagate at the speed of light. And they carry information about changing gravitational fields. And as often happens, the path to our understanding of gravitational radiation has not been completely linear and smooth. Einstein came up with the idea of this just the year after he proposed general relativity itself in 1916. But he had a number of errors in that prediction. He revised things in 1918 and had still one error left, but back and forth he went throughout the rest of his life. Are they real? Are they not? He finally accepted them, but he died some 20 years before there was any evidence that they existed. Now, the features of gravitational waves are they're very, very weak, and we'll talk a bit later about how weak they are. This is the reason that it took until 2015 for them to be detected directly. They only can become strong for binaries when you have massive objects orbiting very close to each other. And what I mean by that is that right now, by waving my arms, I am in fact generating gravitational waves, but not so much that anybody could detect them. And we want to learn about the universe, so these have to be very strong events indeed. They also carry energy away. And if you have a binary, the net result is that the two objects in the binary spiral together. Now, as I indicated, I'm going to show you a brief video, something from Minute Physics, although this particular thing lasts about 3 minutes. My apologies in advance. The person who's giving this video is talking pretty rapidly, but I hope it'll be understanding anyway, and who doesn't love cartoons?
When things move, they create waves. For example, if you shake a stick back and forth in water, you get water waves. Vibrate a piece of metal back and forth really fast, and you get air pressure waves. Shake some electrons back and forth really fast, and you get radio waves. And yes, shake a planet or star back and forth really fast, and you get gravitational waves. Gravitational waves happen because the effects of gravity don't travel outwards at infinite speed. So if the sun were to suddenly jump a few 100,000 kilometers to one side, the changed gravitational field would take time to pulse outwards. And if the sun shook back and forth instead of a single pulse, you'd get continuous gravitational waves. So what's doing the waving? In the case of water, the height of the water increases and decreases at any particular location as the waves travel past. In the case of sound, the pressure of the air increases and decreases at any particular location as the waves travel past. In the case of radio or cell phone signals or any other electromagnetic waves, the electric and magnetic fields get stronger and weaker at any particular location as the waves travel past. And in the case of gravitational waves, the gravitational field gets slightly stronger or weaker as the waves travel past. You can tell a wave has passed by looking at how nearby particles behave. A bobber on the water rises up and down. The electrons in a radio antenna move back and forth because of the changing electric field. And free-floating people or planets or cats move back and forth because of the changing gravitational field. Though in this last case, the peculiarities of gravity mean that the free-floating things actually experiencing the gravitational wave don't feel like they're moving. But if you measure the space between them by sending a pulse of laser light and measuring the time it takes for it to come back, you'll find that the distance between them increases and decreases. In practice, physicists don't actually measure gravitational waves with free-floating cats. They use very, very fancy, expensive mirrors, which are effectively free-floating in one direction because they're hung on pendulums suspended on isolation tables, or which are actually free-floating because they're attached to satellites floating in space, though this hasn't been done yet. The reason physicists need fancy floating mirrors to detect gravitational waves is that the waves are very, very weak. For example, the electrons that vibrate back and forth in a radio antenna to make electromagnetic waves also make gravitational waves. Electrons are matter moving back and forth, after all, but the waves they make are super weak. A 200-watt radio transmitter gives off something like a quadrillionth of a quintillionth of a quintillionth of a quintillionth of that amount of power as gravitational radiation. And that's why here on Earth, we can only detect the biggest, baddest astronomical events, like superfast spinning neutron stars or merging black holes or the Big Bang. Though so far, we've only detected black hole collisions.
Okay, so I hope that was understandable, and that gave you kind of a fun discussion about how cats can be used to detect gravitational waves. We can now think astronomically. What is it that can emit gravitational waves? And this will give us some understanding of what we can learn from gravitational wave detections now and in the future. An important aspect is that it can't be anything static, meaning if you have something that just isn't moving at all, and you ask about the gravitational field, it's static, meaning that if you have your gravity meter your gravity meter will not see any change, and therefore there are no waves. Waves fundamentally come from Einstein's insight that gravity travels at the speed of light and not infinitely fast. So if you have nothing moving, there's no wave. We therefore have to consider what it is that can change the gravitational field and what cannot. And as the video indicated, most things, like me waving my arms back and forth, are incredibly weak when it comes to changing the gravitational field. Therefore, we have to consider how it is that you can get detectable gravitational waves. What are the special circumstances? Okay, so let's think about one case here. And something that may come as a bit of a surprise is that, as a matter of fact, if you have even a tremendously violent event, a core collapse supernova, where you have a very massive star which collapses in its interior, and then there's a bounce and it blows itself to bits, phenomenal amounts of energy. If this is completely spherically symmetric throughout the collapse and explosion, even a supernova, even a collapse to a black hole gives you zero gravitational waves. The basic reason for this you can get if you have taken classical mechanics and have perhaps run into one of Newton's theorems, which is that the gravitational field outside of a spherically symmetric collection of matter is identical to the gravitational field outside that same total amount of matter, the same total mass, concentrated at the center. And this is true even in general relativity and even for moving things as long as spherical symmetry is maintained. Again, therefore, you've got your gravity meter, you've got your eyes closed, you don't know that anything has happened. So this cannot give you gravitational waves. Another thing that cannot give you gravitational waves, although this is not as clear, is that if you have something that is axisymmetric and is rotating around that axis, it does not emit gravitational waves as long as it is not also contracting or expanding. If you think, for example, about neutron stars, one of my favorite objects in the universe, you can have these things rotating hundreds of times per second, but if they are axis symmetric and rotating around that axis, nothing, no gravitational waves. More generally, it turns out that for you to get gravitational waves, you need a time-changing what is called a quadrupole. And that's something maybe you've run into or maybe not. But now we're going to talk about examples of such sources. And in the field, it has become traditional to divide possible gravitational wave sources into 4 categories, which we're going to go through now. Category number 1 is binaries, 2 stars orbiting each other. These naturally have a strong time-varying quadrupole. But remember, that's not enough. It's not just enough to say it can emit gravitational waves. We'd like to be able to have it emit so much in gravitational waves that this is potentially detectable. For that to occur, the objects in the binaries have to be massive and they have to move fast. Now, currently, the gravitational wave detectors on Earth are all ground-based and have sensitivity from tens of hertz to hundreds or thousands of hertz. And it turns out that the only types of binaries that can give you frequencies that high are neutron stars and stellar mass black holes. Not the supermassive black holes in the centers of galaxies, but the ones that are a few times the mass of the sun, up to possibly a few hundred times the mass of the sun. And so far, in the observations performed with LIGO and Virgo, that's all that's been seen. Only binaries, nearly 100 of them, and almost all of those 100 are double black hole events. 2 of the events are neutron stars. 2 of them might be neutron star black hole. Now, by the way, just as a side comment, one of the things that we have to get used to in astronomy is selection effects. It is from the profound philosophical principle that you can only see what you can see. And what I mean by that is that when you consider what it is that has been seen with LIGO, your thought might be, oh my gosh, double black hole mergers must be far more common in the universe than other categories. but that is not actually true. As a matter of fact, double neutron star mergers are more common in a given galaxy than double black hole mergers, but they have significantly less mass, so you cannot see them as far out, and that's why the impression is left that double black holes rule the universe. So this is it. Only binaries, none of the other three source categories, but let's talk about them anyway. Who knows what the future could bring? Hope springs eternal in this as in many other fields. Next category, bursts. Now let's consider a core collapse supernova. And here you might be saying, hold on, dude, didn't we just say those are not going to emit gravitational waves? No, what we said is that if it is perfectly spherically symmetric, it will emit zero gravitational waves. But in reality, the process of the collapse of the core and the explosion involves a lot of turbulence and magnetic fields and all of these other things. Therefore, you do not have perfect spherical symmetry. There is some amount of gravitational radiation that is emitted, but not very much. If you think about the total energy in a supernova, most comes out as neutrinos, a lot of the rest is kinetic energy, much of the rest in photons, and only maybe one billionth of the energy comes out in gravitational waves. It's not easy to see exactly in simulations because they're very difficult simulations. So this means that you're not going to be able to see them very far away. With current detectors, you'd likely be able to see these in some portion of the galaxy, maybe not even the entirety of our galaxy, the Milky Way. In our galaxy, we have a core collapse supernova about once per century. So maybe we'll get lucky. And as we like to say here, this means that you should all eat your vegetables, which is believed to increase your lifetime and your probability of seeing a core collapse supernova. So for what it's worth, when we say bursts, this is an example, but basically we mean something that has a short duration and a complex gravitational waveform, not easily modeled in a precise way. This third source category that is discussed is continuous waves. Now, in contrast, if you have a binary and it's spiraling together, near the end of its in-spiral, when the two things are about to hit each other, it does not last very long, and it changes its frequency a great deal. But suppose we take a spinning neutron star, but we now add a mountain to it. Now that is not perfectly axisymmetric. You can think of the mountain moving around kind of like a little mountain mass, which is orbiting the neutron star, although of course it doesn't have to go with the orbital frequency. It can go much slower than that. Also, these are neutron stars we're talking about. The surface gravity on a neutron star is a few 100 billion times the surface gravity on Earth. And that means you don't have very significant mountains. They tend to be squashed almost flat. As a result, this is a very weak signal, and it lasts a very long time because it's so weak. It's not draining energy from the star very rapidly. So this is the combination. Whereas for binaries seen with ground-based instruments, those are strong signals for a short time. This could be a weak signal for a long time. Maybe we could see it eventually. Who knows? The last category is basically adding up a whole bunch of sources that are each individually weak enough that they cannot be detected, but they can be detected in total. For example, this could be a lot of binaries with individually weak signals. Maybe you have binaries too far to be detected individually, but when you combine them all together, there's a clear noise that you might be able to identify. Arguably, the most interesting of this category would be from the very early universe, from the so-called era of cosmic inflation, when it is believed that the universe expanded faster than the speed of light, but not violating special relativity in any way. At that stage, there might have been a stochastic background, which would be truly remarkable in its importance. So these all have broad signals across a wide range of frequencies. With that in mind, let's now think about some more general characteristics of gravitational waves. So this is a cute little cartoon from my colleague Michela Mappelli, who is an Italian scientist, and she is showing poor Charlie Brown here as a gravitational wave goes by. There is a stretching and shrinking, but it's not just in one dimension. This has to do with the quadrupolar nature that I mentioned before. Basically, if you imagine that my fingers in the ring here are representing a ring of test particles as the gravitational wave goes by, then this ring is going to be deformed in this way, or there's another way it can be deformed like this. So this is like the plus or the cross. And these are tiny, tiny, tiny deformations. These are usually measured in what is called strain. So the strain is the fractional change in length, so this delta L over L. And in ground-based detectors, even a relatively strong gravitational wave will have only a fractional change of about 10 to the minus 21. So there are lots of ways you can compare this. If you had something where the wavelength was about the Earth-Sun distance, 1 astronomical unit, this means that the relative change in that length due to the gravitational wave would be about the radius of a hydrogen atom. So this is not very much. Here is a theoretical indication of what would occur when you have two objects, let's say two black holes spiraling into each other. When they're far apart, they're orbiting relatively slowly, they're generating relatively low amplitude gravitational waves, and that frequency is not changing very quickly. And that's what we see here. We have our wave, which is moving along, but as it gets closer and closer, it has a higher frequency. The frequency changes more rapidly. The amplitude is stronger. Then, when you have the two black holes come together, they make one black hole, and so that reaches its peak, and then it settles down to be a single black hole, which is no longer emitting gravitational waves. This, as I said, is the theory. Now, we can look at the first detection. And the first detection is very much like that. The two different colored curves represent the two detectors in the United States, the two LIGO detectors at Livingston, Louisiana, and Hanford, Washington. And yeah, there's noise, but that is very much what we are looking at here. This was quite a moment for everybody who was involved. Now, I am not, nor have I ever been, a member of the LIGO team, but I can tell you that the timing here is pretty impressive because, as it happens, this was observed in 2015, on September 14th. And in the summer of 2015, I taught at a summer school at the Indian Institute of Science in Bengaluru, little knowing that in just a few months, the very first detection would be made. When it was made so early that a lot of people wondered whether this was a real signal, whether it had perhaps been injected by the team to test responses. But no, it was real. But we're now going to go back a little bit in time. The direct detection of gravitational waves, which, as I mentioned, was September 14 of 2015, was not at all the first evidence that we had of gravitational waves. That honor goes back to the first double neutron star system that was identified. This is a system where you have two neutron stars, and as you may know, in many cases, a neutron star can appear to us as a pulsar, which gives very regular pulses of radio waves, which can be used to time the system, and in particular, to determine whether you have a system which is spiraling in its orbit, as predicted by general relativity. And this and the subsequent follow-up and testing of GR led to the Nobel Prize in 1993. This is called the Hulse-Taylor pulsar, after the two discoverers. And these are moving at about 0.1% of the speed of light. 300 kilometers per second is roughly 10 times as fast as the orbit of the Earth around the sun. The separation is about twice the size of our sun. And as I mentioned, one of these neutron stars appears as a pulsar. This is an extreme system. It's a system where you're able to see a lot of effects that are very weak in ordinary circumstances and much stronger with this system. As an example, some of you may know that one of the early explanations offered by general relativity was why it is that when all other effects are taken out, Mercury, in its orbit around the sun, has an extra precession of its orbit. It's a tiny amount, though. It precesses by 43 arc seconds per century based on this effect. For the Hulse-Taylor system, it's 4 degrees per year, and the orbit is shrinking due to gravitational waves. But that was the indirect evidence. Now, the indirect evidence was corroborated, lots of timing of that system, other systems were discovered. But how is it that you can directly detect the effect of gravitational waves on space-time in changing distances? The idea is that you have small distortions from waves in space-time curvature that show up as weak oscillatory tidal forces. And the person with the vision to believe that this could actually be done was a professor at my institution, the University of Maryland, Joe Weber. Here he is on the right. He's working in the 1960s or 70s on one of his detectors. Now, the idea here is that if you think about binary neutron stars spiraling together, he estimated that near the very end, the wave frequency would be perhaps a few thousand hertz. If that frequency happened to be the resonant frequency of, in this case, an aluminum bar, then it would amplify the signal dramatically, and he hoped to be able to measure the oscillations of the bar. And indeed, in the early 1970s, even the late 1960s, he actually claimed detection. He claimed a number of other detections along the way as well. However, even at the time, there was skepticism that greeted this claim, because even though 10 to the minus 17 sounds like a very, very tiny fraction of change of distance, it's still many orders of magnitude larger than what would be expected. So this was never verified. Other people built bars. They did not see these signals. And unfortunately, this led to a bit of a split. Weber believed to the very end of his life that he had detected this, but this was never accepted. And I can tell you that when I got to the University of Maryland, I met him, I expressed my appreciation of his vision, but he was at that time just kind of bitter that the community had not believed him. But still, he had the vision, and that counts. Now here I'm going to show you a short animation without any sound of how it is that LIGO works. So LIGO stands for Laser Interferometer Gravitational Wave Observatory. And currently the LIGOs that are working are in the United States. What we're going to see on the left here is a laser. The thing in the middle is actually an inclined half silvered mirror so that some light goes through and some reflects. These are mirrors at the end. And then this, which you'll see, is the readout portion. So we start out with our light going through and bouncing in the mirrors, and then part of that light eventually goes to the readout portion. And as the gravitational wave changes the distance, it changes how the light comes back. So here we have the light making its journey to one mirror, and it bounces back. And then the light from the other mirror is coming back, and the light so-called interferes with itself. And how that interference goes is going to affect what you see on the readout on the right. And as you see, as the distances change, the amount of interference, how the waves line up with each other, changes. And as a result, when we look at the readout portion, we have light that comes in and out. So this is, of course, a very simplified version. There are a whole lot of additional mirrors and extremely important tricks that many of the clever experimentalists have come up with. And one of the best of those, by the way, is at Caltech. His name is Rana Adhikari, and he's somebody who has had not just the idea of how to put things together, but the kind of creativity that you need to take the next steps. When the black holes came together on September 14, 2015, this is the first such signal. It was a very strong signal. So people worked really hard at verifying that it was real. And of course, they worked hard on producing animations. So this is an animation that you'll see And the idea is we're imagining it's as if we're close to this system as the black holes spiral toward each other, and there is a background of stars and galaxies. And that background, of course, we can't actually see, but this is what you would see if there were that background. They have done so-called ray tracing in general relativity to see what happens. So let's check that out. So here we have our two black holes, and the apparent spiraling in motion is because of how the light is being deflected. Initially, the two black holes are far enough apart that they were moving comparatively slowly, although in reality, the whole event here took just a few tenths of a second. As the black holes get closer to each other, there comes a point when the two event horizons actually merge to produce a single object, a neutron star, and that is what you would have seen if you were unlucky enough to be really close. Also, you would have been torn apart by the gravitational waves at that distance. So we can be happy we were, in fact, at a safe distance. This has led to a tremendous number of discoveries. We don't even have the fully updated version here. This is an updated plot that is being produced by a variety of people. And effectively here on the left, we have the mass in solar masses. The horizontal axis doesn't do anything in particular. It's just to separate out the events. And for example, on the one on the left, we see that we have a black hole and another black hole merging to form a black hole. Down here, you have neutron stars. And I like this a lot. It demonstrates, among other things, that there's a category of black holes in the roughly 20 to 40 solar mass range, which we had not seen in our galaxy. I also like this because the image here that is made, I don't think intentionally, looks like a bird spreading its wings and about to take flight, which I think is a wonderful metaphor for the science of gravitational waves itself. There were, obviously, in these nearly 100 now events, some that were special. And for me, one of the specialist of the special is the first case where we saw the gravitational waves from two neutron stars coming together. Neutron stars are much less massive than black holes. Your typical neutron star mass is maybe between 1.2 and 2.1 solar masses, and the black holes we've been seeing are often 30 solar masses. This turns out to mean that in the frequency range observable with LIGO and Virgo, you tend to see a very rapid evolution if they're two black holes, and a much longer evolution if they're neutron stars. Here we have a variety of waveforms, and if you can see this, the time in seconds, 0.1, 0.2, 0.3, 0.4. So these are typically lasting a few tenths of a second. But for the neutron star, the time in seconds, 10, 20, 30, 40, it was in band for more than a minute. Very different waveform, very different time scale. And this was a remarkable event. It demonstrated many things, including that at least some of the short gamma ray bursts, which have been known for a long time, come as predicted from the merger of two neutron stars. It gave us information about the dense matter and the cores of neutron stars. It was a treasure trove. When this happened, it was incredibly close for this type of event. A mere 40 megaparsecs, or about 130 million light years, which is a little farther than it is from where I am standing to the corner grocery store. But on astronomical time scales and length scales, this is really, really close. Within 2 seconds of the event, it was possible to see a gravitational wave event and a gamma ray burst. Very different from other events. And eventually people were able to take all this and identify the host galaxy of this event. So this was really, really lucky. But we have a saying, fortune favors the prepared. People had been expecting to see this at some point. And when the gravitational wave event was seen and information was transmitted to a number of groups, everyone who could got out of bed and were observing, and within a few hours, at least a half dozen different groups had managed to find the optical counterpart, and there was a tremendous amount that was learned. If we therefore think about the results of the detections from LIGO in the United States and Virgo in Italy, this tells us a tremendous amount of things. It confirms that black holes really do exist, at least of the kind of pure empty warped space-time. There are always loopholes because theorists are infinitely clever, but they are now a lot tougher to get through. And I'll mention in particular my wife, Cecilia Carenci, who also does work on gravitational waves, black holes, and so on. Almost as soon as the discovery was announced, managed to demonstrate that a particular alternative to black holes called gravastars that people had predicted were dramatically disfavored, pushing them into a tiny corner of parameter space based on even just the first event. So this is the type of very important information we get. It indicated that the way that the two black holes spiral together is as predicted by general relativity. It confirmed, based on the gravitational wave and the gamma ray burst from that particular neutron star event, it confirmed that gravitational waves travel at the speed of light to 1 part in 10 to the 16, if not better. It gave the masses, which were a different category of black hole mass than what we'd seen. So all of this has come just from the first few years of gravitational wave direct detections. But now we want to look for the future. And one of the most interesting near future developments that I'm expecting is LIGO-India. This is going to be something actually using what was effectively a spare LIGO. And it's going to have huge benefits for the worldwide community. Virgo is only about half as sensitive as LIGO. So this means that although you can sometimes see an event with Virgo and the two LIGOs, it doesn't have the impact that it would if it were as sensitive. Well, LIGO-India will be as sensitive as the LIGOs in the United States. Having these detectors separated across the globe not only improves the overall sensitivity of the network, it allows the directional localization of these sources to be vastly better than they would with just the current network. Better duty cycle. The engineers who run these instruments are really good, but they can't keep them on all the time. So what if one is off? Well, if you have more of them, having one off doesn't have the same kind of negative effect that you would otherwise. Of course, people are thinking even further in the future. In the 2030s to 2040s, people are talking about third generation detectors. We are currently in the second generation. These are going to be 10 to 20 times more sensitive than even LIGO is right now. That will allow people to see much greater distances. The ones we do detect, we can detect with far stronger signal, learn more with greater precision. It will be a remarkable advance. In order to now talk about some other ways of extending gravitational wave detections, I just want to give you some quick context here involving physics and gravitational wave frequency. Suppose we have a gravitationally bound object, meaning something like a star or a planet, but not something like you or me. We are now not bound together by gravity. Fundamentally, we are bound together by the electromagnetic force. But big things are bound together by gravity. Suppose it's got a mass m, a radius r. The highest possible frequency is given by this formula. And this is true whether you are generating your gravitational waves by rotation or pulsation or orbits. For a black hole, as you may recall, the event horizon radius is proportional to the mass. So putting it in that formula tells you the highest frequency you can get for a black hole of mass m is proportional to 1 over the mass. Stellar mass black holes, call it 10 solar masses, can be seen with ground-based detectors, which are sensitive to tens of hertz to hundreds or thousands of hertz. However, if you want a supermassive black hole, like the ones in the centers of galaxies, millions to billions of times the mass of the sun, you need to be able to access lower frequencies, and you cannot do that on the ground. Also, although this is the highest frequency for a binary or anything else, you can certainly have a lower frequency If your binary is just wider, then the frequency is lower. Very simple. This means you can see binaries farther apart, and you can see less dense things, binary white dwarfs and ordinary stars and other phenomena. Overall, the gravitational wave frequency spectrum has an incredible range from about 10 to the minus 17 hertz, which is roughly 1 over the age of the universe, to about 10 to the 4 hertz. In terms of orders of magnitude, that is as broad as the electromagnetic spectrum. Now, if we look at this figure, we see that there's a lot of information here. We have, for example, the frequency, again, going from about 10 to the minus 17 hertz to maybe 10 to the plus 4 hertz. You have the detectors that can see them. Right now, we are only able to see roughly 20 hertz to possibly 500 hertz, a tiny, tiny slice of this enormous range in frequency. So that's what we're talking about with LIGO, LIGO-India, Virgo, and so on. And I'm going to talk about other possibilities. In space, we have LISA, which is going to be run by the European Space Agency. Right now, timing pulsars, and possibly at some point when we look at the polarization of the cosmic microwave background. What can produce these? Down here, stellar mass black holes, neutron stars, supernovae, compact binaries, supermassive black holes, also lighter black holes spiraling into those. And there may even be other things as well. So let's first talk about LISA, the Laser Interferometer Space Antenna. This is going to be the late 2030s, currently scheduled for 2037. There are 3 freely falling test masses in orbit around the sun. A whole lot of creative stuff has to be done to make this work, of course, but basically it's going to be sensitive to a much lower range of frequency than what we have now on the ground. This is going to therefore get wider binaries, heavier black holes, and so on. And in particular, we're going to be able to see supermassive black holes from the 10,000 to roughly 10 million solar mass range, spiraling toward each other pretty much anywhere in the universe, maybe even to a redshift greater than 20. So this is when the universe was less than 1/100th of its current age. This can tell us about how black holes merge, how structure forms from a very smooth beginning, a lot of things that cosmologists are drooling over to try to understand. There are many goals from this. When did the first black holes form? How did they form? What was their initial mass? How are they rotating? What is the mechanism of this formation in galactic nuclei? How did they evolve from mergers and accretion? How do you learn about hierarchical assembly of galaxies and so on? Now, this is going to be amazing, but it's not going to be perfect. You'd love, for example, to be able to see a gravitational wave signal from LISA and be able to say, yes, it was that galaxy that hosted that merger. But the positional uncertainties are about 10 square degrees. Now, for context, that doesn't sound too bad because that's about 1/4000th of the whole sky. Sounds like you're kind of narrowing things down. But if you take the whole universe with that solid angle, there are maybe 100 million galaxies in that range. So you need to be able to do other things. You can get a sense for how far it is, so it's not anywhere in that wedge, but it's still going to be a big challenge. Also, because of many uncertainties, the rate of detections are not well known. Another way of detecting gravitational waves goes back to my favorite objects, neutron stars, and in particular pulsars. Rapidly rotating pulsars, the so-called millisecond pulsars, are the most reliable clocks in the natural universe. By looking at these, if there are gravitational waves which are moving by, and here we're talking about frequencies of 1 per month to 1 per decades. If gravitational waves are going by, then the very slight change in the distance to those pulsars produces a little bit of noise in their otherwise excellent timed signals. You have to have tremendously stable pulsars, but they exist, and there's a network of these to try to eliminate systematic errors. The thing is that here, unlike what you have in, say, LIGO, you don't have events. In LIGO, you say, oh, look, whoop, we have this chirp towards high frequency. That was an event. But here, because the frequencies are so low, even the gigantic black holes, say 100 million or a few billion solar masses spiraling around, you're not going to see those individually. What you are going to see is a stochastic background, the accumulation of thousands of these at the same time. This, therefore, is going to give us a different type of information than we have currently. Here's a little demonstration where we have the Earth, and here we have our different pulsars at different frequencies, and they're timed, and as these are moved back and forth by the gravitational waves, the timing of the pulsars is not only changed, but changed in a correlated way. And the 3 pulsar timing array associations in the world, one in North America, one in Europe, one in Australia, together, they are probably already detecting this. But again, it's not a matter like it is on ground-based detectors where you have an event and you see it and that's definite. It's a slow accumulation of data over years. They have not yet seen the correlations between the timing residuals of pulsars that would be the absolute smoking gun. But if it is at the level that it is seen currently, and with that projection, we will know in 5 years. The next method is one that is interesting for its implications and also for the sociology of science that it reveals. We're thinking about here the cosmic microwave background. And to understand that, I want to give you some cosmological context. You know that the universe started with a big bang and expanded. And early on, when the universe was relatively small, it had very high density. That density is such that light could not go very far. It couldn't go across the universe. It would go and hit something very quickly and then bounce off that and hit something else and bounce off that. However, 380,000 years after the Big Bang, it became transparent. And by cosmological scales, it became transparent very quickly. The photons from that era can stream across the universe, and this is true now of photons. Your average photon, let go, will travel all the way across the universe without interacting. This means that we are able to see those photons from that very early stage. Remembering the universe now is roughly 14 billion years old, so 380,000 is a baby picture of the universe. The photons at the time when they were emitted were red photons. They were kind of the typical color of a low mass star. But the universe has expanded and the photons have as well. And as a result, now we are seeing them primarily in microwaves. Therefore, this is the cosmic microwave background. People discovered the cosmic microwave background in 1965. However, because physicists and other scientists are greedy, they don't want to just be happy with what they have. They want to do more, more, more. And people understood that a mere detection of the cosmic microwave background, that was amazing. But wanting to see the structure in it is something that is possible if you have better and better instrumentation. So I'm going to show you the evolution of this. And when you're looking at these, you're looking at the temperature variation. So you have some hot spots, you have some cold spots, but it's useful to keep in mind that these are tiny, tiny variations. The fractional difference in the temperature, around an average of about 2.7 Kelvin, the fractional variation is only about 1 part in 100,000. That's why it took such a long time in order to get this detection. So here we have the map of those variations from the COBE satellite, and then the WMAP satellite, which was roughly a decade later, did significantly better. So you can see there are correlations here, obviously, but WMAP is far better. And then from the European Space Agency, the Planck mission which did even better. So once again, we have excellent correlations, but now we have tremendous precision of information. This has been responsible for transforming cosmology from a joke in terms of precision. We used to have the joke that in cosmology, the uncertainties were in the exponent. But with all of this tremendously precise information from the CMB, or cosmic microwave background, it's possible to measure the universe. It's strong additional evidence for dark matter. It constrains the content of the universe. It just does everything. It sets up the initial conditions. It's wonderful. As I mentioned, how hot or cold things are, this is a change by only 1 part in 100,000. But remember, when we get light, the light doesn't just have energy, which is kind of how you get the temperature. Light also has polarization. And this is something that people are now pursuing very actively indeed. Polarization. Think about a photon approaching you. Now that photon, if it's traveling this way, can essentially have its electric field oscillating up and down, or back and forth, or some combination between the two. This polarization can make patterns. And I'm showing you the 2 fundamental modes. Mathematically, they depend on the symmetries each obeys. And one of them is the E mode. And this is something that is just naturally produced no matter what. But in the early universe, the other type, the so-called B mode polarization, which is something that kind of has a curl to it, for those of you who might have run into vector calculus, this can only be produced by gravitational waves in the early universe. And when would those happen? The epoch of inflation, 10 to the minus 34 seconds after the Big Bang, a time when a lot of the initial conditions were set, but they currently can't be observed easily in a direct way. It would give us a huge amount of information. Therefore, the detection of the B mode in the polarization of the cosmic microwave background would be monumental in its importance. And in 2014, the BICEP2 team announced the discovery of B mode polarization in the CMB. Phenomenal. This is their signal. All these little lines are the direction of polarization, and hots and colds and things like that. This is stunning. It was incredibly fundamental. Visions of a Nobel Prize were in the heads of the team. They went on victory tours. We had a presentation by one of the members of the team, welcome to the gun show, right? Because biceps are guns in some slang. We had a theorist who basically said that the magnitude of this was exactly what was predicted. So everyone was really happy about this. However, you may have noticed the ellipses here. It was not early universe, it was dust. So as I said, in the early universe, the B mode can be only produced by gravitational waves. Late time scattering from dust can do it as well. So dust in the Milky Way, for example. Now, something that you like to say in astronomy is that dust is a 4-letter word. I mean, dust actually has 4 letters, but the reference here is that in English, a lot of your favorite curse words have 4 letters. So when you talk about a 4-letter word, you mean it's a curse word, and indeed it is. So this was not a discovery. This comes to the aspect of sociology. You can ask, what went wrong? They knew, the team did, that dust was a possibility. The best dust map came from the Planck mission, but rather than talking to the Planck people, which would have shared credit, they used a photograph that one of the BICEP2 team members had taken of a Planck dust map at a conference. So they should have talked to the Planck team, and eventually they did, and then they used the real data and discovered this was dust. Also, there was a lot of pressure to publicize. Something like this would probably get a Nobel Prize. The institutions involved obviously wanted to be part of that. These things happen. Scientists are human too. People are now doing much more sensitive experiments, and the original so-called discovery has been ruled out by a lot. It wasn't right. One aspect of this that's a challenge, going back to the claim the theorists made that this is exactly what was expected, It isn't, and it wasn't at the time. Basically, if you see this, it's a tremendous fundamental discovery. If you do not, it's not very meaningful because there's no way of predicting the amplitude. It could be there, just not detectable by any mission in the next century. So overall, and in conclusion, when you think about gravitational waves in the future, by the mid-2030s, we will have super versions of the ground-based detectors we have currently that are 10 to 20 times more sensitive. The worldwide network will localize bursts. It will have a better duty cycle. We'll have stuff on a higher fraction of the time. In space, we have LISA with its many implications. Pulsar timing arrays, we might have a signal right now. So either in a few years, the champagne will pop or people will be disappointed. The B-mode polarization, it's an exciting possibility and no guarantees. Overall, gravitational wave astronomy is a huge development in our understanding of the universe. I feel profoundly honored to be able to do some work in this field at the time of the discovery, and I hope that you share my excitement. Thank you very much. I'll be happy to take any questions now.
Okay, so we have a few questions from YouTube. I'll read those out first. Thank you, Paul. That was very well done. I think we all enjoyed it a lot.
Thank you.
So here are the questions. The first one is, do gravitational waves follow superposition as other waves do?
They do indeed, yes. There are many aspects of gravitational waves which are quite familiar to our ordinary study of waves. One way in which this could be relevant, you may know that the gravity of some mass can lens waves, lens, say, light, and that can bend things around and get multiple images. In principle, this could happen with gravitational waves, and then depending on the exact nature of the lensing, you can have interference and diffraction and other wave effects.
Okay, we had one more from YouTube. So you said earlier that when two supermassive black holes are rotating, and if we were to be standing right next to them, the gravitational waves would tear us apart. But the same gravitational waves when they're detected on Earth are very minuscule. So just how much is the decay that gravitational waves experience as they travel through the universe?
Yeah, it's a great question. The deal here is that what we detect is the amplitude of the waves. When we think about detecting electromagnetic waves, we think about the flux. So the flux is proportional to the square of the amplitude. And therefore, in the same way that flux decreases like 1 over the square of the distance from the source, the amplitude, like the square root of the flux, decays like 1 over the distance, so not the distance squared. So in some sense, depending on how you phrase it, it decays less rapidly with greater distance. But the flux of gravitational waves does go like 1 over distance squared. The amplitude, however, like 1 over the distance.
Okay, now if there's anyone here with us in the Zoom call who has any doubts, feel free to speak up.
I see some questions in the chat. Should I read those out, or should we have the people who asked them read them out?
I'll read the ones out here for now. Others you can speak up, I guess. So first one we have is, are we gonna prove or disprove the existence of primordial black holes with LISA? Is that possible, or is that a goal?
We are not going to be able to prove or disprove the existence of primordial black holes with LISA. And part of the reason is that there is tremendous uncertainty about the mass of primordial black holes. They could be anything from 100 mountain masses to 1 billion solar masses. In many ways, a lot of that mass range has been ruled out. One of the windows that remains is, perhaps coincidentally, somewhere in the vicinity of the masses detected with LIGO and Virgo, meaning a few solar masses to a few tens of solar masses. LISA would be more sensitive to the really high mass ones. So if we say, what about LIGO? There is a better chance that eventually detections using LIGO, which is sensitive to the high frequencies of those lower mass black holes, we may be able to do that partially by looking at gravitational lensing. If you have a lot of primordial black holes, then events behind them can be lensed. But there's a lot of discussion about how likely this is, and probably it's going to be difficult to completely rule them out.
Next, we have, can the super accurate measurements from LIGO be used to map the bodies in space?
If by map the bodies in space you mean localize the direction, it'll be better than what we have now, but still terrible compared to ordinary astronomy. Therefore, if we want to figure out the galaxy associated with a given merger, we probably need help from electromagnetic astronomy. If by map the bodies in space, we're thinking about the structure of the bodies, one of the things that excites me is the possibility that when you have enough double neutron star mergers, you're going to be able to learn things about their structure. For example, how dense they are in the center. And that, I think, is quite an interesting possibility.
Okay. And the next one, we've already kind of gone through this, but do gravitational waves undergo damping? Which is...
They do, but not very much. If you have, just as an example, if you have a core collapse supernova, the gravitational waves will leave as if nothing is there. Even neutrinos interact a little bit. However, we know they have to undergo damping because they can interact with our instruments. And by moving the instruments back and forth, they have a possibility of producing a little friction or something in the instrument. So that energy does come from the gravitational waves.
Next one we have is, can we say that the CMB is equivalent to our understanding of the
observable universe? What we can say is that the epoch of the cosmic microwave background was the earliest stage in the history of the universe when we could receive light. There are other aspects which in principle we could see earlier, and one of those would be the influence of gravitational waves from the time of cosmic inflation. If we think about neutrinos, although very difficult to detect, in principle, those could be seen back to maybe 1 second after the Big Bang. So when it comes to light, yes, that's the farthest that the observable universe extends for us.
Hello. And am I audible?
Yeah, you're audible.
Yes, Dr. I wanted to ask whether SHM of big mass objects like planets, do they create gravitational waves?
The audio was not great on that question, my apologies. One thing that might actually help, if you don't mind, is if people write in the chat, then I'll be able to see it for sure. And then I'll be very happy to answer the question. Thank you. Does the simple harmonic motion of planet-sized objects create gravitational waves? Okay, so by this I assume you mean the orbits. Yes, it absolutely does. And for example, if we think about the Earth around the sun, I believe that it would spiral into the sun based only on gravitational waves within something like 10 to the 30th years. So don't hold your breath. Is there a range of mass for which gravitational waves are created? Not really. Any mass that moves in such a way that the quadrupole changes, the reduced quadrupole if you want to be technical, will generate gravitational waves. It's not going to generate much unless it's really massive things moving quickly. So again, I'm generating gravitational waves here, but you're not going to see it with anything. Also following up on the damping question, what causes this damping in gravitational waves? I do like to think about this in terms of simple energy conservation. If you have gravitational waves go by, then those gravitational waves are going to be moving things back and forth. And if they're at all connected with each other, then that is going to produce a certain amount of energy by friction or something else. So it has to be that the gravitational waves are damped. Then we have, why doesn't the collision of black holes create gravitational waves? It does. It absolutely does create gravitational waves. What we've talked about here are binary orbits, but if you start your two black holes far apart and spiral them together, they're generating gravitational waves. And then when they come together and they merge and form one black hole, it's all producing gravitational waves. And at the end, when it's going from a deformed, merged black hole to a final black hole state, then it's kind of shaking things off like a dog shaking itself off of water. That's the ring down motion. So all that absolutely does produce gravitational waves. We have a cosmology question here. What is actually expanding in the expanding universe? It's space-time itself is expanding. And this is something that is very counterintuitive, I have to admit. When we think of the universe expanding, we think of the evidence of looking at galaxies. Almost all galaxies appear to be moving away from us, and the farther they are, the faster they are moving. It's natural to think of this as if they're leaving from us, like we have some kind of cosmic bad breath, which means that they don't want to be near us. But anyone in any galaxy would see the same thing. You can think of this as imagining that each galaxy, to some extent, is tied to the expanding space-time. So locally, nothing is moving faster than the speed of light, but if we have two things far enough apart and the space-time is expanding fast enough, they can move faster than the speed of light away from each other. And if that's the case, we cannot see them, which means that this observable universe that we have in photons out to the cosmic microwave background is not at all likely to be the totality of all there is. There's probably a huge amount, maybe an infinite amount beyond that horizon. Okay, next question. Just as ripples are created in a water body by throwing a rock, can space be thought of as made of some liquid like matter with black holes and neutron stars replacing the rocks creating gravitational waves? That is an interesting point. If we think about the rock and going into the water, as we saw in that early video I showed, it's going to create water waves and ripples. And in that case, what you need in order for the ripples is a medium. You need the water to be able to ripple. When it comes to gravitational waves, it is space-time itself. And space-time itself you can think of as empty space, but it also is affected by gravity. So if you like, you could kind of think of space-time as a medium in which things are rippling. Can bodies like asteroids obstruct the readings to be received, or a body big enough to block the waves? The answer is yes, but not very much. And what I mean by that is, think about the gravitational waves, think about some gravitational wave going through an asteroid. Now what it's doing is it's stretching and squashing the asteroid. And in doing so, the rock is being moved, there's friction within the rock, and as a result, you end up with energy that is lost. But it's a tiny, tiny amount. Remember this strain or fractional change of 10 to the minus 21. Now think about moving rock by that much. You're not going to deposit a lot of energy, but you can deposit a little bit at least. When stars collide, the collision creates a pulse. Is it a gravitational wave? If it is, can a gravitational wave of super high intensity create a disturbance for a planet or any major mass in the universe? Yes, if stars collide, then you generate gravitational waves. You have mass moving in such a way that you will produce gravitational waves. So the other part of the question kind of flips that around. If we had, let's say, a double black hole merger that was merging within the solar system, then the amplitude of the waves coming past the Earth would be enough to shake it, presumably very rapidly, and this could have a fairly high intensity. Now, would this create a major disturbance? It would if it were close enough. If you're really, really close to a merging black hole right at the end, the strain is 10%. It's not 10 to the minus 21. So imagine getting vibrated by 10% at a frequency of 100 hertz. It would be very painful. I mean, you'd die, okay? But much farther than that, and it's a negligible effect, which means it's also tough to detect. We say that gravitational wave effects on masses can be considered negligible, but if we go down to the scale of electrons or even more fundamental particles, do they have some effect on them? The effect on them is even less. And the reason is that, remember, we're thinking about a fractional change in distance. And I've talked in terms of 10 to the minus 21 being that fractional effect, but think about a wave, a full wavelength, right? That effect is 1 part in 10 to the 21. But if we're talking about something like 100 hertz, then that's going to have a wavelength of 3,000 kilometers. So that's the whole effect. Now imagine you zero in on that, like 1 centimeter. Then instead of having the whole effect of the wave, you have a very, very small fraction of that effect. So it's even less important for the really tiny things. And when you get to atoms or fundamental particles, there's just nothing going on.
Okay, so we have a few more questions from YouTube. Let's read them
Okay.
out. So, do gravitational waves affect our readings for cosmic background radiation? Should be.
So do gravitational waves affect the cosmic background radiation?
Our readings for cosmic background radiation. So how we would perceive them from here.
I see. The answer is yes, but at a level so tiny that it's absolutely negligible, fortunately.
We have one more. So what is the limit of our observable universe? Would it be the past when the universe was opaque and moving away from us, or something else?
Yeah, the limit to our observable universe, when you're thinking about cosmology as a whole, you can really think about this in terms of time as well as distance. If we ask how far, let's say, a photon has traveled since the beginning of the universe, it's about 13.7 billion light years. If you think about the distance traveled by a photon from the cosmic microwave background, it's that minus 380,000 light years. It's almost the same thing. So what we can do is we can think about how far back could we see with any mechanism whatsoever. And as far as we know now, it's back to close to the Big Bang. How close to the Big Bang depends on the cosmic messenger. For photons, it's 380,000 years. For neutrinos, it's 1 second. For gravitational waves, it might be 10 to the minus 34 seconds. So that's how we think about the limit of our observable universe. I see that we have another question in the chat, which is, do gravitational waves change their path like light does when it enters a different medium? And here we can say yes, if we're thinking about an analogy. I mentioned gravitational waves. So imagine you have a mass, say the fist here, and we have gravitational waves which are traveling along. They can get gravitationally deflected. And in doing that, they do change their path. And there are ways you can formulate this to be kind of like an index of refraction, although there probably are better ways of doing that to get the best insights.
Okay. So I had a question myself. So as I was reading through your papers when sending you the emails, one thing that particularly struck me was the consequences that research into this field would have on modern science as a whole. And there's a part where you write that it could possibly disprove general relativity. So, like, how far what could be the possible implications that research into gravitational radiation could hold for us?
Yeah, that gravitational radiation, and we're just, remember, beginning the phase of gravitational wave astronomy. For example, the possibility of disproving general relativity. If we look at the gravitational waveform from black holes spiraling toward each other, for example, well, right now, general relativity does very, very well. But maybe a more sensitive instrument will show clear deviations. That would mean we have to rethink our theory of gravity. Maybe it would be a hint toward quantum gravity, which is very difficult to get at in other ways. It could be that we get evidence that although general relativity may be right, that the objects we're thinking about are not actually black holes. Maybe they have a surface. This has been restricted very much in terms of possibilities, but maybe there's still some small possibilities. In terms of understanding matter, the cores of neutron stars are in a state we cannot reach in any laboratory on Earth. It's too dense, it's too much neutrons per proton, and so on. And by looking at neutron stars spiraling together, the effect on the gravitational waves can be inverted to try to understand some things about neutron star cores. Other things, again, the properties of gravity itself. And I'd also like to mention some things that are perhaps a little bit more practical, because certainly I hope that you are as interested as I am in the science of gravitational radiation. But there are some people who don't really care and they want to know practical benefits. So let me give you some ideas of how those benefits can be practical. The process of constructing the laser interferometers like LIGO-India has given people a motivation to do much better in their laser physics, in mirrors, and in also the algorithms needed to get these sorts of signals detected out of noise. So all of these are things that could be used very much in the future. And sometimes this happens. Sometimes you end up with a purpose which has never existed before, and it requires much greater sensitivity. And this has happened before in astronomy. Just as a random example, the X-ray detectors that are used at airports originally came because people wanted to do X-ray astronomy. So as a result, we now have X-ray detectors at airports. Lasers themselves, the original idea came from Einstein in 1917, and nobody really cared about that for a long time. Lasers were developed, and it even took some decades before they found many practical applications, and now they're everywhere. So these are some things to think about. So we have, I guess, a comment on one of my previous questions. This is in the chat again. The refraction of the light is because of effects of epsilon. So this is in the electric field equation. So this is the permittivity, which would change the magnitude of one component, which would be exact reason for refraction of gravitational waves. Okay, thank you. We have another thing here. Although off topic, I have a question. I've heard that the space-time fabric deforms near huge masses. Hypothetically speaking, if we have a mass large enough to almost make the space-time fabric touch the other end, will it be possible to have a wormhole there? Wormholes are a fun subject. So for wormholes, if you think about the deformation of the rubber sheet that I mentioned, where you suppose that the rubber sheet is deformed so strongly that it basically goes to a point, that would be like a black hole. If instead it reaches a minimum throat width and then comes back out, that would be a wormhole connecting different parts. Is it possible to have a wormhole? It's tough to know. There are some studies that were done by Kip Thorne and his colleagues, and also Igor Novikov and his colleagues, which seemed to demonstrate that in order to have a wormhole that you can go through, so you don't want one where you go through it and immediately collapses and kills you. To have one you can go through, you need what is sometimes called exotic matter, which weirdly has a negative energy density. And that sounds ridiculous, but there are some things you can point to in laboratories that would have that property. The problem is that if you can have a wormhole, you can have a time machine. You can go backwards in time if you have a wormhole. People have investigated this. It's possible that stuff just naturally going through the wormhole would feed back on itself because of the time machine aspect and would shut the wormhole down. We don't know whether this is true, and until we know whether it's true, we can still enjoy watching the movie Interstellar.
Thank you so much. I think we're done with questions for now. So I think we're concluding the session. Thank you so much, Paul, for taking time out of your, not out, a very busy schedule to come here. I think I speak for all of us that it was thoroughly entertaining and educational, and we were definitely able to pick up quite a lot. And thank you for being so patient with the questions.
My pleasure. Those were wonderful questions. Thank you so much.
It was a great experience for us, and as mostly freshers in an astronomy club, I think it was very inspirational.